Hi, I want to explain this simulation, that is about oscillatory motion. In this case, it's just a simulation where we're going to reproduce some wave on a string. So remember that we have transversal wave and longitudinal wave. In this case, in this experiment, we work with some transversal wave, right? So when you go over the experiment, right, that is this lab 5.1, they ask you to put the damping in 0, in none, and they say just to put the tension of the string in high. And well, we're going to activate the rulers, okay? And we're going also to, in this case, use a fixed n, and we're going to use oscillate. So we're going to make this to oscillate. So they will ask you in this case to fix the amplitude, to start changing the amplitude for the frequency of 1.60 hertz. And then on this constant frequency, they ask you to start modifying the amplitude and see how this amplitude is affecting the wavelength, right? So you should put this in a slow motion, otherwise it will be very difficult to measure wavelength and all this. So what do you have to do if you want to measure the wavelength for this amplitude, for example, of 0.60 and this frequency of 1.60 hertz. So remember, we are not going to change at all the frequency. So we'll stop your let me wait that these just be more stable. So you can stop here, for example, when this green ball is at the level of this reference line, and using the ruler, you can measure the wavelength. So the wavelength is the distance from this point to this point, right? Approximately. This is your wavelength. So you can measure your wavelength here. And the wavelength looks to be like approximately 4 centimeters, right? I would recommend you to, repeat the experiment two, three times to make sure, because there could be some variations, right? It looks much better like that. So it's much better when you have a symmetric wave, right? I mean, that is completely symmetric, that have the same amplitude, in this case, both oscillations have the same amplitude. But if you go and you measure the wavelength, it's not going to differ too much. It's just going to be approximately 3.8. In the time that we measured, it was like approximately 4. So it's like a 3.8 centimeters. The wavelength in this case is this distant, with the distance of a complete oscillation, right? Or the length of a complete oscillation. So the distance from this point to this other point over here, this other intersection with a reference line. I will later increase the amplitude to 0.75. And then I will just start again. Now I will, of course, wait that these just be an unstable oscillation, right? So just be waiting for a little bit. And then you stop it to measure. It's not a good time to measure yet. No yet. Let's try to just be pretty symmetric. And then you can also measure the wavelength from this maximum to this other maximum. So it didn't change too much. It looks like it's again 4 centimeters. The other time was like a 3.8. And we just keep this oscillating for a little bit more. I will measure again. And again, I go like a 4 centimeters. So here I had a wavelength of 3.8 in the first case when it was an amplitude 0.60. Later for 0.75, I go like a 4 centimeters. I will increase then again the amplitude now to 0.90. And I will just start again. Make sure to have a slow motion, if not, it will be very difficult. I will measure now the wavelength. And again, I got approximate to 3.8, 3.9, right? So we see how increasing, in this case, the wavelength, the amplitude, we are not changing too much, really the wavelength, right? But you should collect the data, and later you can just calculate the speed of the wave based on this, right? And then you have just to follow your data and just make your observations and just make comments based on the data. Later, you will reset this. So you will reset the problem. And then what you're gonna do is to have a fixed amplitude. I will stop it. I will have an amplitude of 0.75. And what I'm gonna do is to start increasing the frequency of the oscillations. You will start with a frequency of 1.40. I will put a slow motion. I will activate the rulers, right? And then I will just start just making the measure of the wavelength in this new case for different values of frequency. So again, I will try to look for the exact moment to stop, to make my measurement. This one looks pretty symmetric. It's not that symmetric, so we can wait a little bit more. So you can measure the wavelength here, and you get a wavelength that is approximately like a 5 centimeters. I will just continue it for a little bit more to see, to corroborate that this is the value. I will get 4.8, 5. It's not that symmetric. I will try just to wait for an instant where this be really very symmetric. Oh, I forgot to eliminate the damping. So that's why. You can measure the wavelength here. So always make sure you have no damping. So you can measure a wavelength from this maximum to this maximum, or this frequency of 1.40. So I got like a 4.6 approximately. 4.6 centimeters is more or less the wavelength in this case. I will later increase the amplitude, the amplitude of the frequency to 1.60. And then when we increase the amplitude to 1.60, I will later stop again here. And then I will measure the new wavelength for this new frequency. And now the wavelength, that is the distance from this point to this point, is like a 4 centimeters. But I can just keep doing this again. So I can measure this again. It shows like a 4.6. I will increase now, increase now the frequency. So I don't change the amplitude. And I can measure the wavelength. I go like a 3.8, 3.9. It's always good to, measure a couple of times. See again, we got the same thing, like a 3.7, 3.8. And like that, you can increase your frequency more to 2.10, later to 2.40. And with the ruler, you can measure the wavelength. So remember that the wavelength is the distance from 2 consecutive maximums, 2 consecutive minimums, or 2 zeros that are in phase. So for example, from this point to this point, you will never measure a wavelength from these 2 points that are consecutive zeros, because these points are not in phase. This one is going up. Here, the wave is going downwards. So you must look for 2 points that just be in phase. So for example, this point and this point. So when you measure over the reference line, over the zero, you should leave one zero in the middle. So it's between 2 maximums and between 2 minimums, or leaving 1 0 in the middle, between 2 zeros in phase. This is how you measure your wavelength. So basically what the report or the practice asks you to do is to just do that. I mean, in the first case, you have a constant frequency and you will start increasing the amplitude. You find the wavelength. Remember, the wavelength is being measured with the rulers, and later you will find the speed. Remember, then you know that the speed is the product of the wavelength times the frequency. And well, you will comment on your observations and you will say how the amplitude affect or not the wavelength and the speed of the wave. And later in the second part, you have just the frequency that is going to change, and then you have a constant amplitude of 0.75 centimeters. So you will again measure with a ruler the wavelength, and with that later you will calculate the speed again, and you will observe your result and just write based on those observations, what happened with the wavelength and with the speed when you change the frequency. This is basically what the lab report is about. The simulation is a simulation where you have to be patient when you are working with the simulation, and try to be as accurate as possible, making your measurements. So that's basically, what I wanted to explain you. So I hope that with this video now you will be able to complete your work, and submit your lab report. Thank you so much.